Is she presenting first?
Yeah,
Okay.
full screen share.
Yeah, I don't see anyone on there yet. So. Or Yuli is you? YULEI2?
That might be the student.
Okay. I'll go up there and just wait until see if she comes on. What was her Android ID again?
Mine.
Oh, no, the one who's presenting.
So HAOJIX.
HOJI. Okay. I'll take a look for her.
Okay. Hi, everyone. We'll be starting in a couple of minutes. Till then, please download the notebook from the Piazza post. And just to recap, so this Lab 11 is on transformers, where we learn about the transformer architecture and components of that. And it'll mostly be a lot of hands-on coding, and I would suggest everyone to go back and watch lecture 19 on transformers again if there is any doubt in the fundamentals of transformers. And yeah, think we can start.
Sure. Hi, Shita, can you hear me?
Yes, you're all.
Cool. Let me share the screen. By the way, is that recording right now?
Yes, we are recording.
Okay, cool. Can you see the collab screen right now? Can you see my screen?
Yes, it's visible.
Okay, nice. Let's get started. Hi everyone. My name is Judy, and welcome to the recitation for Transformers. Sorry, I had like a really serious fever, so I had to take it online. Yeah, but like for the first part, we will introduce you the basic concepts for the Transformers, and the reference will be mainly about like this really famous paper called Attention is All You Need, where it introduces the concepts to calculate the attentions, as well as the basic transformer architecture, and we will go through them one by one. So first one, for the transformers, there are actually several components. So for example, the first one is the word embeddings. That is, we know that like for the transformers, the input can be the text, right? And how will the text be converted into the transformers? Then we need to convert them into embeddings. So it will be the representation of the words in the form of vectors so that they are able to capture the features of the language for the text tokens, like the word meaning and the context. And the second one is the encoder decoder models. So we know that for the transformers, we can have it either have both encoder and decoder or decoder only. And I know that like currently for the most popular transformer architectures, so for example, like GPT-5, Cloud, um, Q3, these kind of models are all decoder onlys because for like the chatbots, we only need to process the input sequence to convert them into the embeddings and then directly calculate the attention and go through the MLP layers and finally get the output of the logics without the encoder. However, we can still have the encoder, which its function is to process this input sequence to capture the feature representations, that is the embeddings of the text tokens. And the decoder, just as what I have just said, is to use this output of the encoder to sequentially compute the output sequence from scratch, like a autoregressive decoding procedure. And because like for the chatbot, we mainly need to have this process to do the autoregressive decoding. So sometimes people just like don't use this encoder as much. But let's still introduce like how the encoder works. So here's the basic architecture. But to be honest, like for this architecture from the paper, it's like really old. And for the most latest transformer architecture that people are using right now, they are changing this where the um, layer normalization is. So right now, like just want to let you know, people are one sec. People are mainly using um first the input embedding as the input, and then they do the positional encoding, and then they do the layer normalization first, and then they go into the attention layer to calculate the attention, and then they do a residual add, and then do another layer normalization, and then go through the feed forward layer. And the reason why people are doing this right now is because for the layer normalization, they can get the gradient more smooth so that the gradient update can be done more um, like smoothly. So that's why people are changing this transformer architecture. But in the original paper, here in the architecture, people are first using the attention calculation and then doing the residual add and the layer normalization. Yep. So for the encoder, for the input pre-processing, we'll have this input as the text tokens, the embedding layers, as well as the position embeddings. So when we have the text, how are we gonna convert them into the embeddings, right? This is the first step. So we are doing this thing called tokenization, which is to convert the words to the numerical representations without losing their meaning and context so that the model can capture the features from the input tokens. And the first step that we do is we create the vocabulary list. Like here, mm, we have a vocabulary table with each word, or maybe we cannot just have it as a word, we can have it as like several parts. Um, so it depends on how you want to tokenize your input tokens. And the basic meaning here is that for the for each element in the vocabulary table, we're mapping them into some indices, like the numerical token. So for this, like input text, like when you play the Game of Thrones, and then for like each token, we will try to find the numerical value in the vocabulary table, and then like map them to get this um embedding. Yeah. So this is the process for the tokenization. Yep. So this is basically how the input embedding looks like. So we have like different tokens, and then we go through this input embedding layer, and finally we will have several vectors. And the second part is called positional encoding. So why we need this positional encoding? Because we know that when we are calculating attention, we are calculating the relationship between like different tokens, right? However, we don't know like where these tokens are inside this input sequence. So for example, if we use LSTM instead of transformers, they will process them sequentially one at a time, so the information of the order will be preserved. But the advantage of the transformers is that they are processing them in parallel, so that the compute speed can be increased, but we are also losing track of the word order information. So, and it is very important because if, for example, the word not, the order is changed in the sentence, and actually it can means very different things, even though all the other parts in the input sequence are not changed. So that we want to have this position embedding to create this order information and then add them to each word embedding. Uh, So what we are doing is that the conventional method is to use this sine cosine function. But actually right now the most popular method is using rope. So because that is for because for like here for the position embedding when we're calculating it, it is depending on the absolute order in the sequence. However, like in rope, we only capture the relative order relationship between the tokens so that when we are using this method, the model can know the relative relationship instead of the absolute relationship of the order, and they can generate the tokens uh, like and have a better performance. So the basic idea here is that for the position embedding, we will use some methods to calculate them to show that the relationships of the order within the tokens in the input sequence, and then we will like directly add them to the word embeddings that we just show you, like here, for example, for the input embeddings. After we have these, and then we calculate the position embeddings, we'll just like add them together as the input of the transformer architecture. So after we get the whole input embeddings, that is the tokenized tokens like vectors, as well as the position embeddings, then we will go into the attention layer. So firstly, we want to know that like what is attention? So attention is basically the relationship among the different tokens in the input. So there are several types of attention. The first one is called self-attention. So self-attention is that it, it is the attention that the encoder or decoder pay to themselves, and in computing their respective outputs by paying attention to their own context. So for example, in the encoder, they pay attention to the adjacent inputs of this particular token itself, and the decoder pays attention to the previous outputs. So self-attention is basically you calculate the attention of yourself, which is the current token, with all other tokens in the input sequence. And for the across attention on the other side, it refers to the attention that the decoder pays to feature representations of the inputs derived by the encoder. Things like each individual output can relate to some parts of the input than others. What does it mean? So it means that, for example, we have like two different modalities. We have some input embeddings for text, as well as we have some input embeddings for images. And we want to calculate the attention between these two embeddings. Then we will use cross attention to capture the relationship between the text embeddings with the image embeddings. So this is called cross attention. It is not just to capture the relationship of itself with the other tokens in the input sequence. So another thing that we are commonly used in the transformer architecture is called multi-head attention. So what is this and why we are using it? Multi-head attention is just actually a combination of several self-attention head, where each attention head focus on different linguistic features of the input. So what does it mean? Actually, it means that when you are calculating the attention, we are doing, um, for example, Q equals to WQ, that is the weight matrix for query, right? Multiplied by the input X, as well as we have K, the key value, the key equals to the WK multiplied by the input embeddings X, as well as the value matrix. We have V equal to the WV multiplied by the input embedding X. And here what we are doing is that actually we are calculating the attention and trying to capture the features in some other spaces. So we're trying to like map the input embeddings to some other spaces. And um, the um, the theory behind multi-head attention is just we have different self-attention heads. So we have different WQ, WK, WV matrices that we can map the input embeddings into different spaces so that we can capture the features in different spaces. And then finally, we will project them and do the concatenation to get the final attention value. So it means that it can better capture like different features in different spaces so that we can get more like useful information from the input embeddings. And also another good thing about multi-head attention is that we can do this calculation in parallel. So it saves like a lot of time for compute. Oh yeah, here. So it's just like what we said. We can look into the figure again. Excuse me. Yeah, so actually this is the way that we calculate the attention. So as what I just said, we have the carry vector, we have the key vector, we have the value vector. That is the QKV. So here first the input is that the input embeddings consists of two parts. One is the text embedding, one is the positional embedding, and then we add them together. And then we have the query, we have the key, we have the value, and then we multiply by like a weight matrix and then get the query key value matrix. And then how to calculate attention? We first calculate the query multiplied by the key transpose by taking this dot product, which we call matable because it is like a matrix multiplication to get this attention future. That is the attention scores. Like here, we calculate the Q multiplied by K transpose to get this attention future. And then after we get this value, we will do the softmax. So what we are doing is that we are first dividing the matrix by the dimension of the key vector, which is the dk, and then we will do this softmax to calculate the attention and then to make the results be in the range of 0 to 1. And then finally, the filtered value is then derived by taking a dot product of multiplying by the original value vector. So this is the full calculation for the attention. That is, we first calculate the Q multiplied by K transpose, and then we divide it by this decay, and then we do a softmax, and then finally we multiply by the V value. So this is the attention calculation for just one attention head, right? And for multi-head attention, so for example, in this paper, like the attention is all you need, we use like 8 multi-head attention heads. Then we have um several attention heads in parallel doing the same thing. We have the same input embeddings, and then we map them into like different spaces by multiplying by different weight matrices and doing the softmax divided by the decay, and then finally multiplied by the V value. And as I what I've said, because for different attention heads, we are mapping them into different spaces, so that finally we need to do another thing, that is we need to concat them together and then pass through a linear layer to give the final combined output of the multi-head attention layer. So like here, we have the output of different attention like attention scores, and then finally we'll concat them and then go through like a linear layer to map to the same space and get the final output of the multi-head attention. Yeah, and after we calculate this attention layer, then in this transformer architecture, it is added to the residual connection of the original like position aware input embeddings. And the reason why we are doing this residual thing, it is because we don't when we are updating the gradient and doing the backward, we don't want to lose the original information. And another thing is that if we are doing like massive, like even like when we are going through some attention layers or like MLP layers, and even if the changes are not very huge, the original input's information is still preserved by adding the residual connection of the original input, right? So that we don't need to care about that, okay, the gradient update might be a problem, and we cannot update the gradient because we are still preserving at least the original information of the input before without going into the attention layer or the MLP layer. So that's why we're doing this residual add. Yeah, so this is for the residual add, and then after the residual add, we're going through like a linear normalization, and currently mostly we're using the RMS norm, and we're changing the position where the layer normalization is placed. But here what the linear normalization means is that we're like subtracting the mean and then dividing by the standard deviation. And then finally, we'll go through like a feed forward layer, which is called the MLP layer. And in this MLP layer, we'll have the linear layer, and then we will go through like a ReLU or JeLU activation function. And then we'll also add to the residual connection from the multi-head attention output and then do the layer normalization. And this is the like how the encoder block works. Yeah. So this is basically the two parts. One part is that we calculate this attention, and then we do the residual add and the layer normalization, and then we go through the feed forward layer, and then we go through another layer residual add and linear normalization. So this is the whole encoder, how it works. And also, yeah, and just like one note for the MLP layer, like usually we have two layers. So that's why we first have like a linear layer here. We multiply by some matrix W. We have maybe like WX multiplied by B. So that is the simple MLP layer. And then we go through some like activation function, nonlinear activation function. And then we go through like another linear layer. So usually the feed-forward architecture has like 2 MLP layers. Cool. And then for the decoder, actually it's very similar. So basically is that if we have the encoder, and then the decoder will just like take the inputs from the encoder. And then another thing is that also the positional embedding for our like target sequence. And then it will also calculate the attention. So this output embedding will be divided into the query and key. And then we will still go through this multi-head attention layer. Yeah. And for the value vector, excuse me, like here, this is the target sequence that is passed directly to the decoder's mask multi-head attention layer before being used together with the query and key from the decoder for the multi-head attention. So why we need this mask? So what the decoder does is that they are doing autoregressive decoding, right? So they are generating token one by one. But the thing is that when we are generating the second token, we should only base on the information for the first token. And then after we generate the second token, we will add the KV values for the second token into, for example, the KV cache or somewhere. And then based on the information for the first token as well as the second token, we will generate the third token. So what this means is that because of this autoregressive order, we should only care about the tokens that we have seen before and not the tokens in the future. So that's why we are using this mask multi-head attention. So implementation wise, in this mask multi-head attention layer, the future tokens are masked with like minus infinity during this self-attention before we compute the softmax of the query and key. So it is just like actually it's just like yeah, it's like this. So it's like we are only care about this left bottom triangle in the matrix and we cannot see the future tokens. So we are just like mapping them as minus infinity. Yeah. And the reason why we are mapping the future tokens to minus infinity is because while we're calculating the softmax for the attention, all the future tokens will go to 0 so that we will only focus on the previously predicted tokens instead of the future tokens. So for example, like here in the mask attention future, we will have all of the softmax values as 0 so that it doesn't affect the calculation of the attention. Yeah, cool. So this is the basic concepts for the encoder and decoder. And you have any questions, feel free to ask on the Zoom chat box or send me a message on Piazza or email me. Thank you so much. Yeah, I will hand to Ishita.
Let me see, I'm not doing something right. That should be great. Sharing on Zoom.
Okay.
Yeah, no, it really needs to be up here, there's no.
All right. Let's code up these parts that Judy just discussed. So just please run these setup cells. You might see some dependency issues, which I was like trying to debug right now, but I think this works. But okay, let's start with. So we'll start with positional encodings, and to basically learn how to code the positional embeddings, we will be using this multi-30K data set. And this is a machine translation and description data set. So it has image descriptions in German and in English, and German to English translations. Yeah, so, okay. This is how the data set looks like, the multi-30K data set. And okay, let's move on to, so first, we would be tokenizing the data set that we just discussed. So these are some library functions that we are using, the get tokenizer library, get tokenizer functions from the Spacey library. And to get the tokenized strings for both the English and the German text in our data set. And then we create a vocabulary from that. So so throughout this notebook, there would be like 10 checkpoints that we will complete. So this is just the code that we have already provided for you. So I'll just go through it quickly. Okay, so here we are just building our vocabulary. So when we are preparing our data for training, and for that, we will be adding these tokens. So the padding, start of sequence, end of sequence, and any unknown tokens if we have. So we'll be assigning them special tokens. Yes, and I will just run and show you in a minute, but please feel free to run this. Oh, am I audible on Zoom? I just see the chat. Judy, could you confirm if I'm audible? Oh, okay, got it. Okay, I think this should be better. Sorry for that. So I'll just repeat what I went through right now. It was just going through this multi-30K data set, and this data set you can check out online the details about it. We are just using it to see how the positional encodings actually work. And right now we first tokenized it, and then we are creating a vocabulary for it by adding the padding, start of sequence, end of sequence, and unknown tokens, assigning them special tokens. Is my screen not shared?
Yeah, it's on Zoom.
Oh, okay. So, yeah, the notebook should be shared on Zoom. Oh, are you guys not able to open the notebook from Piazza? Okay, maybe I'll. Oh, okay. I'll just post the link in the comments. This one maybe. Um, okay, please let me know if this also doesn't work. I'll see if there is some. I'll just do it. I'll just change the sharing link. Okay, so after we have the vocabulary, we write our dataset class. And there's nothing new in this. We have been doing this for all our homework P2s. So there's a collate function, there's get item, and oh, okay, it still doesn't work. Oh, okay. Okay, thank you so much for confirming. Okay, so this link works. Got it. So yeah, this is just the normal dataset class that we have been creating for all our homeworks. And moving on, we just load the dataset here. Please go ahead and run these cells. I have some yeah, I have some import errors here that I will look into. Um, but if anybody is able to solve this, please post in the comments in the Zoom chat. So, okay, so we went through the tokenization, vocabulary, data loader, and yes, so the this brings us to the first checkpoint of this notebook. That is, how do you code up these positional encodings that we talked about? So these are positional encodings are basically to um, let for the transformer to recognize relationships between words. So currently, the transformer without the positional embedding is really good um, at processing multiple inputs at once, and it's very fast and efficient. But without positional encoding, it's not able to uh, find the relation between different words and how uh, in long sequences words relate to each other. So that's why we assign sine and cosine frequencies for every position by this formula, and the numbers 10,000 and 2i by d model, this mostly came empirically. If you are more interested in to looking at it, you can read the paper. I can attach that in the student notebook or in the solution notebook. And this is the absolute positional encodings. And as Judy also mentioned, that we also have different kinds of positional encodings now. This is the most famous one because it was mentioned in the Attention is All You Need paper, where transformers were first introduced. So the first checkpoint is basically um, initializing the sine and cosine positional embeddings using this formula. We have already uh, made this position of sequence length, this position array of sequence length, and also the div term. Div term is basically 1 upon 10,000 and to the power 2 I by d model. This is already given to you, so it should be pretty simple. I'll give you guys maybe 2 minutes to figure this out, and then we can move on. We already have the forward pass for positional encoding written here. And yep, you guys can start coding and let me know if there's any doubt on this. Don't know what's wrong with this. Okay, so I'll just write this. So this is torch.sign and our position to the div. Okay, so that was simple basic absolute positional encoding. Let's move on to the self-attention mechanism. We'll just be using some dummy input to check our dimensions here. And So we are initializing the query, key, and value vectors. We have our D model default value set as 256. And I'll give you a few minutes to think about what should go here and try coding it yourself. Think about the computation that's being done in the self-attention mechanism block. Okay, so as DK has the same dimension as our model, that's D model. So we can just initialize it. Or just directly, we can use D model here. Okay, so this matmul block, what do we think it should do? It should basically uh, output the store the product between the key and query and key values. But as we see that we, yeah, just Okay, I hope everyone is following till here. Um, so that's the matmul block, and now we will calculate the scale output. So as we discussed, for us to find the similarity, query and key multiplication is enough, but to actually learn something and not to prevent vanishing, the problem of vanishing gradients, we divide that we call scaling the output. We divide it by square root of dk. I think there's a lot of lag in my notebook, so okay. Okay, so we calculate our scale output. So to have the self-attention mechanism, we multiply key and query. We scale it. We divide it by square root of dk, and then we apply the mask for softmax, which we have already implemented for you. Okay, moving on to the third checkpoint. So self-attention, it turns out to be that it's not enough to just query, just to assign one query for each word, so each token. So we want one word to have multiple meanings. Maybe they are, maybe an apple is a fruit at the start of the story, and maybe it's referred to as a snack or something else, uh, as a red object later on in the story. So we want to assign multiple queries um, for the same token. That's why we use multi-head attention. So you can just think about multi-head attention as not increasing the computation, but actually parallelizing it. So how do we do that is uh, how we define the head dimensions. So when we initialize multi-head attention, we consider the number of heads that we want, and we want to basically have our head dimension into number of heads equal to my D model. So I want to basically divide or bifurcate my D model into num heads number of head dimensions. So yeah, that's your next to do, to just fill in these code lines where you calculate what the head dimension should be and then what your DK should be in this case. And also, please get started on how you reshape the query key and values. Like this is what we learned in the lecture as well, that our Q, K, and V are of 3 dimensions. That's the batch size, the sequence length, and the D model. But to use it for multi-head attention, we want to make it 4-dimensional, and we want to add the heads also in this. Okay, so for calculating the head dimension, as we discussed, we are dividing our D model into number of heads. And now my dk becomes the dimension of one head, that is the self dot head dimension. And then just initializing the query key and value, it remains the same here. And in the forward pass now, we want to reshape our QKV to 4 dimensions to make it compatible for the multi-head attention. So I'll just use q.view for this. Okay, so when we are bifurcating into multiple heads and we are calculating our matmul and my scale output, at the end, after softmax, we want to reshape back to 3 dimensions. So that's the next to do.
SAQ line.
Here. Okay, moving on to the fourth checkpoint, that is the position-wise feed forward. This is where the actual learning is happening, and we use the ReLU activation function for this. And yeah, here we just need to
Add that activation.
activation. So we just add dropout for like regularization here, and these values that you'll see currently, they are just dummy values, but what we want to achieve from this lab is basically the exact code computations for coding the exact computations that happen in the transformer architecture. Okay, I think that this was fairly easy. Okay. Let's move on to the next block that we talked about in the architecture. I hope everyone has, like, it would be great if everyone can open the actual attention is all you need paper, or just keep going back to this transformer model architecture that was proposed in that paper. So we know that where we stand currently in our implementations. Okay. Okay, so here we just need to create a residual connection, and we need to normalize per layer. We have talked about this a lot of times during lectures and during this lab as well, that why do we need these residual connections so that our training is more stable and our gradients are not lost. So yeah. Okay, so this was just the implementation of layer norm according to the formula that's mentioned in the notebook as well. Okay, I hope everyone is following. Moving on to the sixth checkpoint. Now we finally come to the encoder block. So what we want to do here is we want to initialize the self-attention, the norm layer, the feed-forward network, and then a norm layer again. So for this self-attention, we want to use the multi-head self-attention here instead of the basic self-attention that we learned, because that is also what everyone uses now, and nobody uses just the basic self-attention. So these were the two arguments that we passed into our self-attention class, the model size and the embedding size and the number of heads that we want to initialize it with. Add a norm. So from this encoder block, now we want to forward pass our input. Okay, so that is just simply calling. Okay, sorry. Yep. Let's move on to the next checkpoint, that is the decoder. So here we also go through the same process. This is how our decoder um, block looks like, and we initialize the self attention, the MHA block, add a norm, encoder decoder attention, and then these layers again. I will actually leave this for you guys to fill. I think it should be uh, pretty simple. So because we are predicting predicting in the decoder block, we have to add masking here. Okay, I'll just leave some code as hints in the notebook. Okay, so yeah, this is what the causal masking that I was talking about that takes place. So when our encoder is learning for, let's say, the machine translation tasks, we want to learn from the future as well. We want to learn from basically the whole sequence. So we have a bidirectional mask, but when we want to predict things, then we don't want to cheat. We don't want to look at the future before predicting it. So yeah, that's what you do in the decoder block. Okay, so here are some mask visualizations. I'll just see if I already have some output blocks. Okay, I hope everyone is done with the checkpoint 7. Okay, so torch.tril, this is something that we use uh, to easily apply the causal masking. And you can read more about this. I think there are many versions of this, depending on if you want to apply mask in the lower diagonal uh, or the upper diagonal of upper triangle of the matrix. So yeah, look at this method. This is what we are using here. So So in the beginning, as if you remember, we added some padding. We assigned some special tokens for padding for unknown characters for SOS and EOS. So basically, we want to ignore those padding tokens completely at this stage. Okay, so when you run the completed notebook, you'll be able to see the exact mask that you created here. Um, here I have. Okay, I don't have an image for that right now, but um, oh, okay. Here it is. So this is your source mask, and this is how your target mask will look. So this was done basically by using this torch.trill function. Okay, so we just coded up our encoder and decoder fully and the blocks inside it. That's the positional embeddings, multi-head attention, feed forward, and add a norm. So now we just need to call all of these blocks individually and initialize and forward pass through our transformer module. So we already passed the vocab size for the source, for the target vocabulary. We just need to call torch.embeddings here. And yeah, we define the positional encodings. In the interest of time, I'll just leave it as a practice for you guys. And yeah, I'll make sure to post the transformer cell and the solved notebook on Piazza as well. Okay, so these hyperparameters are just some dummy values to um, check the sanity of your code and to check if all the dimensions were correct for your transformer implementation. Um, you can run this on your own and please check the checkpoint boxes on Piazza when you're done with your checkpoints. Okay, so I also have some optional code at the end of the notebook for vision transformers. Please feel free to look at it. I'll be skipping it for this lab today. But yeah, that was it. Please let me know if you have any doubts. And thank you guys for showing up. It's almost towards the end of the semester. And yeah, all the best.